A very good afternoon, students. Today we will be learning all about ionic radii. In my previous lecture, I have told you about covalent radii, metallic radii and van der Waals radii. And in this lecture, we will be talking about radii of the ions when they are present in a ionic crystal. So the topics I will be covering here are what is ionic radii, then factors affecting the ionic radii, periodic variation of ionic radii, and then I will tell you about the methods to determine the ionic radii values and some related problem. From the name itself, you can understand that ionic radii corresponds to the radii of ions in a ionic crystal. And in a ionic crystal, we can measure the internuclear distance between the nucleus of the anion and the cation by using F-ray diffraction. And we can get the internuclear distance that way. But if we divide the internuclear distance or in ionic bond length by 2, it will not give us the radius of the anion or the radius of the cation, because the radius of anion will be much bigger than the radius of the cation. So there are some indirect methods to determine these ionic radii values that I will discuss with you later. But you should know that these ionic radii they are actually dependent on the environment they are present. That means they will be affected by the other ions or other interactions present in the crystal lattice. So first let me tell you, let me give you an idea about the radius of cation and an anion. So what happens when a cation is formed from a neutral atom? The radius is less than the neutral atom, and when an anion is formed, the radius of the anion is much bigger than the neutral atom. So why this is happening? Because you see here I have taken the example of sodium and sodium plus and chlorine and chloride minus. So in sodium we know the atomic number of sodium is 11. So number of proton in the nucleus is 11, and in the neutral atom the number of electron is also 11. But when we remove one electron from this neutral atom, Na plus will be formed, and in that number of proton will be unchanged, so it will be 11 in number, but number of electron will be less than what there were in the neutral atom, so it will be 10 in number. So the same nuclear charge will attract less number of electrons, so obviously the attraction force will be more and the size will be less. And in case of this chlorine to chloride minus, what happens, you see, chlorine is having atomic number 17, and so the number of proton in the nucleus is 17 and number of electron also is 17 in number. And when this Cl minus is formed, so one electron is more in case of Cl minus. The nuclear charge remains the same. So here also proton number was 17 and here also the proton number was 17. So as the number of electron becomes more, so the nuclear charge felt by the electrons will be less because of more number of electrons, and so the ionic size is more than the neutral atom. So in case of cation the size decreases, and in case of formation of anion the size increases. I hope this is clear to you now. So here I have taken few examples as well. You see here when cation is formed, M2M plus electron, the atomic radius of lithium is 1.52 angstrom, whereas the ionic radius of Li plus is 0.60 angstrom. So this is much less than the neutral lithium. And in case of sodium, it is in neutral condition, it is 1.86 angstrom, but when it is a cation, that is Na plus, the radius is, ionic radius is only 0.95 angstrom. In case of formation of anions, I have taken the example of Cl and Cl minus. So here you see the atomic radius of chlorine is 0.99 angstrom, whereas that of chloride is 1.04 angstrom. So this is more than what we had in case of the neutral chlorine. And if we take the example of sulfur and sulfide, you can see in sulfur the atomic radius is 1.00 angstrom, whereas in case of S2 minus the radius, ionic radius value is 1.84 angstrom. So this is much greater than what we had in case of neutral sulfur. So we can say that from these values that when a cation is formed, the radius decreases, and when an anion is formed, the radius increases. So now I will be discussing with you a very important point. What is that? The size of the isoelectronic species, how this dictates the ionic radii value. So here I have taken some of the elements, like you see here I have hydrogen, helium and lithium. So and here are the other elements, and here another series is here, and you see here the oxidation states are written here. So when hydrogen is in -1 oxidation states, its electronic configuration will be 1s2, and helium, you know, its electronic configuration is 1s2, and lithium in +1 states, its electronic configuration is 1s2, and the ionic radius values are written here. So first let me tell you about this series. So what is happening here? The atomic number for these elements are increasing here from hydrogen to helium to lithium. So what is happening? The Z star value basically increasing, because as the number of electrons are same, so the sigma will be same for all these species, but Z star will be different. Z star is actually increasing. So as the Z star is increasing, so you can understand the attraction towards the outer electrons exerted by the nucleus will be more, and so the size will decrease. So here you see the ionic radius for this H minus is 150 picometer, whereas for helium it is 120 picometer, and for lithium plus this is 66 picometer. Now if we compare this series, here you see we have nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium and silicon. Here nitrogen is present as N3 minus, oxygen as O2 minus, fluorine as F minus, and then neon in neutral condition, and then sodium Na plus, and magnesium +2 state, aluminium in +3 state, and silicon in +4 oxidation state. And the electronic configuration for all these species will be 1s2, 2s2, 2p6. But you can see the trend in ionic radius, this is decreasing, 150, then 140, 136 and so on. We are not comparing the value for neon because neon is actually in neutral condition. We are talking about the ionic radii, so we will not basically consider about helium, neon, argon, because we don't get the ions for these elements. So if we compare here, you see the value is decreasing, and again if we compare here, the value is decreasing. So what is happening here? The same thing, that Z star value is increasing because their number of electrons may be same, but the number of proton in the nucleus is increasing as the atomic number are increasing as we are going from nitrogen to oxygen to fluorine, or sodium to magnesium to aluminium to silicon. That's why the size is decreasing. The same thing is happening here. They are also isoelectronic. If phosphorus is in -3 state, that means P3 minus, S2 minus, Cl minus, then argon 0, potassium +1, calcium +2, scandium +3 and titanium +4 oxidation state. This is their electronic configuration, and Z star will be increasing. So this chart or this table is very important for you, because many a times actually questions come from this end. So in the problem they ask that compare the sizes of O2 minus, F minus, Na plus, Mg2 plus, or explain the trend in ionic radii of S2 minus, Cl minus, K plus, Ca2 plus and titanium 3 plus. So first you get confused as there are mixed type of species, some anion, some cation, some there are mixture. So you first of all think that how we will be comparing, but if you look critically you will understand that these are isoelectronic species. So take the Z star values, you don't have to calculate, just say about their atomic number and then compare the radii values. Now let us compare the size of the cation of an element in different oxidation states. So I have taken here the example for iron. So here this is iron 2 plus, then iron 3 plus, then iron 4 plus. And you can see the ionic radius value for iron 2 plus is more than that for iron 3 plus, and it is more than that for iron 4 plus. So what is happening here? The same reason, actually the size is decreasing because as the atomic number for iron is same, so the number of proton in the nucleus will be same, but number of electrons in the outer cells will be less as we are going from iron 2 plus to iron 3 plus to iron 4 plus. That means due to the increase in the nuclear charge, the size will decrease and obviously the ionic radii value will decrease. So along a period in the periodic table, what happens? Actually there is a decrease in the ionic radii value. So what happens, you see in case of Na plus, sodium plus, the value is 116 picometer. For magnesium 2 plus it is 86 picometer, and for aluminium 3 plus it is only 67 picometer. So what is happening, as they belong to different groups, they have different oxidation states present here, Na plus, Mg2 plus and Al3 plus. So as the charge is increasing, we have already seen that as the cationic charge increases, then also the size decreases, and again here the charge in the nucleus, that means the positive charge in the nucleus is also increasing, so the size is decreasing. And if we take in case of, you see the oxidation state is fixed in case of scandium 3 plus, then titanium 3 plus, then vanadium 3 plus, you see here also the value of ionic radii is decreasing due to increase in the effective nuclear charge. Here I would like to tell you about another effect which is shown by this 4F and 4F and 5F series of ions, where in the same oxidation state, that is in plus 3 oxidation state, there is a very prominent decrease in the ionic radii value, and this is described as lanthanide or actinide contraction. And you see in case of lanthanide 3 plus, it is 117 picometer, and then gradually the value is decreasing. In lutetium 3 plus it is 100 picometer. So why this is happening, I'll discuss with you in detail about lanthanide contraction. And here actually what happens, because of the incorporation of F electrons, F electrons are very poor shielder of nuclear charge, so the effective nuclear charge, that is the attraction force towards the outer electrons, is much more due to the presence of the poor shielding F electrons, and so the contraction in the size of the ion takes place, and this is a very prominent effect in lanthanides and present also in actinides, and they are called lanthanide and actinide contractions. Now I will tell you about how the value of ionic radii changes along a group. So you see here, in case of lithium plus, the value is 90 picometer, in sodium plus it is 116 picometer, and in potassium plus it is 152 picometer, and in rubidium plus this is 166 picometer. So from this series you can understand that as we are going down in group 1, the value is increasing, and in case of group 17 also you can see the value is increasing. So you can I hope you will be able to answer why this is happening. I have shown you here pictorially how the values are gradually increasing as we are moving from top to bottom in a group. You see, these are the atomic radii value, and you know very well the reason why the atomic radii value increases as we go from top to bottom. So the same reason is true in case of ionic radii as well. You see, this is in group 1, then in group 2, beryllium 2 plus, magnesium 2 plus, calcium 2 plus, strontium 2 plus, the same trend, and in group 3 also, in case of aluminium 3 plus, gallium 3 plus, and indium 3 plus, the same trend could be seen. And the reason you know very well, as the number of cell is increasing as we are going down, although the nuclear charge is also increasing, but the increase in incorporation of new cell is more prominent and the size increases. So here you can see the example of the halide ions, the same thing, as we are descending in the group from fluoride to chloride to bromide to iodide, the value is, the ionic radii value is increasing due to the incorporation of new number of electron cells. So here also the atomic ionic radii of some of the elements are presented, and here you see in this part, left part of the periodic table, the metals are present, so cations are formed here, and in the right side where there are non-metals, the main ions which are formed are basically anions. So it is difficult to compare these values with the right side values, but we can compare among these anions or among these cations. And here you see, as we are going down, the ionic radii value is increasing. It's true in case of cation, and it is true in case of anion as well. And you see, if we compare period wise in between the cations, you see the size is decreasing from Na plus to Mg2 plus, from potassium to calcium 2 plus, rubidium to strontium 2 plus, or cesium plus to barium 2 plus. So here the size is decreasing. This is the normal period wise change. The next point I'll be telling you about the coordination number, how the coordination number of an ion dictates the ionic radii values. So here I have taken the example for lithium plus. In picometer, you see, if the coordination number of lithium plus is 4, the value of ionic radius is 73 picometer, whereas if the coordination number is 6, the value is 90 picometer, and if the coordination number is 8, the value is 106 picometer. So what is happening, as the coordination number is increasing, the number of ions surrounding the cation is increasing, and there will be a repulsion in between those ions, and there will be an effective increase in the ionic radii value. And the same trend you can see in case of sodium plus ion. So here the value is 113, and then gradually it is increasing. Now another point on which the ionic radii value depends is the spin multiplicity. So this you will be learning later, but here you just see the values. Like iron can be found in two states, high spin state and low spin state, in both in iron 2 plus and in iron 3 plus. So in iron 2 plus, if we have the high spin configuration in coordination number 6, the value for ionic radii is 78 picometer, but when we go for low spin state, the value is only 61 picometer. And when iron is in +3 oxidation state, in high spin condition, the value is 65 picometer, but in low spin condition, this is 55 picometer. So you see, when we are going from high spin to low spin state, the ionic radii value is decreasing. That is true in both the cases. So what is high spin and low spin? You can see the electronic arrangement. The maximum number of electrons are unpaired in case of high spin state, and in low spin state, the pairing up of the electrons takes place actually. So here you can see that we can say, if we go from high spin to low spin state for any species, the ionic radii value will decrease. So from the electronic arrangement also, you can say how the value is increasing in case of high spin state. It is occupying more space than in case of low spin state, and that's why the ionic radii value is more in case of high spin state. So as I have already told you that there is no direct method to determine the ionic radii of any cation or anion, but here I will present to you two methods which gives us the ionic radii value for many ions, many cations and anions. The first one is the Goldschmidt method. And what is that? Goldschmidt assumed that in crystals formed by larger anions with small cations, like for example Li, where Li plus and I minus ions are there, and this Li plus is having very small size compared to the bigger I minus. So what happens? The anions touch each other, and if they touch each other, we can take the interionic distance between these two anions, and if we can divide that by 2, we will get the ionic radii value for the anion. And if we can get the value for an anion like I minus, then we will be able to determine the values for many cations. Interionic distance of this anion, that means here for example with I minus, with larger cations, that means with Na plus, K plus, etc., the salts here is sodium iodide, potassium iodide, will now provide us with the radii of the cations in Na plus and K plus. So from Ni or Ki, we will get the interionic distance, that means the bond distance, and from that bond distance value, now if we subtract the value for I minus, the radii value for I minus which we got from here, we will be able to get the cationic radius for Na plus or K plus. Here you see I have shown pictorially two large anions, they touch with each other, and this distance will give us, if we divide this by 2, we will get the value for the ionic radii of the anion. So this method is an indirect method, and with the help of this method we can get the ionic radii value for many cations. So for small cation surrounded by large anion A, Ra, that means the radius of the anion is equal to daa divided by 2. This is the distance between two A minus ions. For example, we have taken Li plus I minus, that means lithium iodide compound, and here R minus is equal to internuclear distance. So Iaa divided by 2 is equal to 426 divided by 2, so is equal to 213 picometer. Now we have taken the example of potassium iodide. So here you see the ion, the cation is large in size. So the anions present here, I minus, they are not touching each other. But from here we have got the value for the ionic radii value for I minus. So if we now know the interionic distance between K plus and I minus, which is 353 picometer, we will be able to determine the Rk plus, that means the ionic radii for K plus ion. You see here Ri minus is equal to 213 picometer from here, and so Rk plus is equal to 353, that is interionic distance minus the radii of I minus. So it gives us the radius for K plus is equal to 140 picometer. So this way we can determine the ionic radii value for many cations. Another very important method to determine the ionic radii value is Pauling's univalent method. So scientist Pauling, he actually chose some isoelectronic and univalent crystals. So here he chose sodium fluoride, potassium chloride, rubidium bromide, or cesium iodide, etc. So here you see all the ions, they are univalent: Na plus, F minus, K plus, Cl minus, Rb plus, Br minus, and Cs plus, I minus. So they are univalent, and the cation and anion is isoelectronic. Now he first told that in the solid state the ions touch each other. Thus, the internuclear distance between the cation and anion is equal to the sum of their ionic radii, that we know. So, D is equal to Rc plus Ra, where Rc is the radius of the cation and Ra is the radius of anion. Now, he told that the radii of a series of isoelectronic ions vary inversely with their effective nuclear charge. That also we know, that R varies as 1 by Z star. If Z star is more, then the R will be less, and if the Z star is less, then the R will be more. And he told that R is equal to Cn square divided by Z star, where Z star is equal to Z minus sigma. Z star is the effective nuclear charge, and then sigma is the screening constant. So in the equation, Ra is equal to Cn square by Z star. Cn is the proportionality constant determined by the total number of electrons in the noble gas configuration attendant. When anion or a cation is formed, they achieve the noble gas configuration. And in case of isoelectronic system, the Cn values are same. So for the cation or the anion which are formed, in both the Cn value will be the same. So we can say that Ra is equal to the radius of anion is equal to Cn square by Za star, and then Rc, that is the radius of the cation, is equal to Cn square divided by Zc star. So now if we make Rc by Ra, what happens? This becomes that Z star A divided by Z star B. So what is that? Because we have seen here the Z star values are inversely proportional. So now you understand how this equation is coming here. It is Rc by Ra is equal to basically Z star A by Z star C. So anion, the Z star value for the anion, and then Z star value of the cation, and as Z star A is equal to Za minus sigma A, and Z star C is equal to Zc minus sigma C. So here it is wrongly written sigma B, it should be sigma C. So we can incorporate these values here and we can get this equation. So the another equation we have is D is equal to Rc plus Ra. So from these two equations we will be able to solve, and we will be able to get the values for Ra and Rc. So we will be able to calculate the values for Z star C, that is for the cation we will be able to calculate the Z star value, and for the anion also we will be able to calculate the Z star value, because using Slater's rule we will be able to calculate the values of sigma A and sigma C. Then putting these values here we will get the ratio for Rc by Ra, and after putting this in the second equation, and if we know the value for the D, we will be able to find out the radius for cation or anion. And then if we subtract that value from the internuclear distance, interionic distance, we'll be able to get the value for the other ion. So the problem comes from here is like calculate the Rna plus and Rf minus values in sodium fluoride if DNAF, that means the interionic distance, is equal to 2.31 angstrom. So I think you will be able to solve this using these two equations, but still I will explain this to you. So Na plus and F minus, they are isoelectronic species. In sodium neutral, we have the electronic configuration 1s2 2s2 2p6 3s1, and in Na plus this is 1s2 2s2 2p6, and again in F minus the electronic configuration is 1s2 2s2 2p6. So these two species are isoelectronic. Now we will be able to calculate the sigma for this. This I have told you previously using the Slater rule how we can calculate the sigma, and the sigma value here is 4.15, and the sigma value will be same for both Na plus and F minus. Now we will be able to calculate Z star separately for Na plus and F minus. So we can put these values in the equation 1, and we can get, see here the atomic number, that means the nuclear charge of sodium plus is 9. This is fluorine. Fluorine is 9, and in case of Na plus this is 11, and we are subtracting the value of sigma 4.15 from that, and we get these values, and the ratio becomes 0.748. Now we have already it is given that DNAF is equal to Rna plus Rf minus is equal to 2.31 angstrom. Now we have Rna plus is equal to 0.748 into Rf minus. So we can put instead of Rna plus we can put this. We are writing here instead of Rna plus 0.748 into Rf minus. So now solving this equation will give us the value for Rf minus. Rf minus equal to now 1.322 angstrom, and we have the DNAF value, so it is 2.31 angstrom. So now if we subtract from 2.31 the value for Rf minus, we will get the value for Rna plus, and this becomes 0.988 angstrom. So now I think you will be able to answer the questions as you have learned how to determine the ionic radii value. Using this method you will be able to answer the problems related to this part. So today we have learned what is ionic radii, then we have also learned the factors affecting the ionic radii, and we have also learned the periodic variation of ionic radii, and we learned two methods, Goldschmidt and Pauling methods, to determine the ionic radii values, and I have also discussed with you a problem related to the determination of the ionic radii value. So I think you will be able to answer the questions related to these topics, and today I am finishing my lecture here, and thanks for watching my lecture, and I will see you in my next class.